This is an introduction on how to find derivatives for logarithmic functions. Check out that we have two types of logarithms: natural logarithms and logarithms with any base. This a, it's a constant, it's a number. A logarithm can have any base: base 10, base 2, base 5, different bases, like base 2 in this example we have on the right. On the left side, remember that a natural logarithm, it's a logarithm base e. But to simplify this, we call it natural logarithm. So these two formulas are very alike. Actually, the only difference is this section right here, when we are finding the derivative for a logarithm with a base a, with any constant as a base. So let's start with the more simplified formula, the one on the left side, the natural logarithm. The only thing you need to identify when you have a logarithm is the argument of the logarithm, because that is the one that you're going to have in the answer of the derivative. Check out that you should take the argument and find the derivative alone of that argument, that it's u derivative, over the argument exactly the same. The denominator should be u, exactly the same. So what should happen in this example on the left? Y derivative, it's equal to. So you identify u, you identify your argument, and you would say, okay, if that it's u, 3x, how much it's u derivative? With power rule, we know it's 3. With that information, we have more than enough to find the derivative of that natural logarithm. The derivative would be the derivative of the argument, 3 over 3x, the argument exactly the same. Remember that because of the minus, we have two sections in this first derivative. The left side is the natural logarithm, and the right one is just an algebraic part. So we're just going to use power rule to solve that. So the derivative of that section is minus 2. At the end, before finishing, we do want to simplify whatever we can. In this case, I'm going to simplify those 3's, but we should simplify and write in order depending on the exercise we have. That is the answer for the one on the left side. What happens, right, when we have a logarithm, not natural logarithm? Check out that it's almost the same. We have u over u derivative. So that argument, it's exactly the same in the denominator, the derivative of that in the numerator, that part is the same. We're just going to add in the denominator the natural logarithm of the base. That is really the only difference. So for this exercise, any constant that it's multiplying, remember that 5 is just going to stay there multiplying. The part that we're always like changing or finding the derivative of is the section with x's, with variables. So actually for this second derivative on the right side, the 5 is just going to stay there. And what's going to happen with that logarithm base 2? We identify u, we identify the argument, and we say, okay, if that is u, what would be the value for u derivative? The derivative of the 3, the constant, it's 0, and the derivative of minus x squared with power rule, it's minus 2x. So that section, that u derivative, is in the numerator, minus 2x, over the argument exactly the same, 3 minus x squared, and we're just going to add the natural logarithm of the base, in this case of 2. I check, can I simplify anything? Can I like write this in a little better way, more order? That 5 can actually multiply the minus 2, so multiply those, the binomial and the natural logarithm. If you want, you can do it, but in this case, I'm just gonna leave that multiplication marked because there's nothing that I can actually simplify. And usually, if we check the order, we should have first the algebraic function and then natural logarithms. I'll talk about the order in functions in our next video, but this one would be the final answer for the one in the right. So check out how easy it is. It's really all about identifying the argument and finding that derivative alone. So have these two formulas very present and you should be able to solve any natural logarithm or logarithm with a constant base. I'm going to show you really quickly two exercises already done just for you to compare. In this case, this one it's a product rule from the very beginning. Why? We have an algebraic section and we have a logarithmic section. So we have two different functions. One is a logarithmic function and the other one is an algebraic. And because these two functions are different and they're multiplying each other, we must use product rule to solve this exercise. U and B, identifying the product rule to substitute it here. Remember that. And once you find, how do we find the derivative of U? Power rule, right? It's just an algebraic function. And remember, to find the derivative of that natural logarithm, you just identify the argument that it's 6x, and the derivative of 6x, it's only 6. The argument exactly the same, it's in the denominator, and that's the only thing we're doing. That's what the formula says. Derivative of the argument over the argument. And we simplify it as 1 over x. Once you have that, you substitute u derivative and b derivative in the product rule, and just to finish, we write it in order and we simplify whatever we can. Check out that it's really not that complicated going from the product rule to the actual final answer, but just be careful. You must check your order and you must check if you can simplify anything. We can even add one more step in this one. We can actually even write a common factor. What is a common factor on that one? 6x. 6x appear in both. So actually, an even better answer would be with a common factor, just to check if we can simplify anything even more. So if we do that, we would have 2 times the natural logarithm of 6x plus 1. And that's even a better answer, but both are fully correct. But we would check at the end. Let's try to check at the end if we actually have a maximum common factor. To finish, let's just compare this exercise with another one. Because this one, the product rule is at the very beginning. Check out, from the very beginning, you see that there's a multiplication of an algebraic function and a natural logarithm. You see it from the very beginning. But let's compare with the following one. In this one, at the very beginning, you only have the logarithm. There's no product rule at the very beginning. But when you want to find the derivative of that logarithm, you would say, okay, the only thing I need to identify is this argument. That argument, exactly like that, should be in the denominator. You have it right here. It's exactly the same. But we need the derivative of this argument in the numerator. So at the moment that I want to find the derivative of that argument, I need a product rule. I need to identify u and v. I need to apply a product rule to find the derivative of this argument. So check out the difference. This one, the product rule comes afterwards. When I'm finding the derivative of the logarithm, at the moment I need this derivative, the inside of the natural logarithm, I need to use product rule. Comparing with the last one, the product rule is at the beginning, is the first formula. And then we have power rule and the rule for logarithms. But the product rule is at the very beginning. And in this one, the product rule comes afterwards. The product rule comes when I want to find the derivative of this inside of the logarithm. Check out that you have u and v derivative right here. Check it out with your own time and with your own formulas. But pretty much it's power rule to find u derivative, and to find the derivative of b, because it's a root, we need chain rule. That's this derivative, I found it with chain rule. Once you have that, we substitute. This is just a substitution in the numerator. It's just a substitution of the product rule. And once we do that, you do have to check the simplification. Like, this is the derivative for sure, but we do want to simplify that. In this case, I'm splitting this denominator. I'm assigning it for both of those polynomials in the numerator. I'm splitting it. And the reason that you have, check out exactly that denominator, it's in both. It's the same denominator. But the reason I'm doing that is because right here, you have exactly the same parentheses with the same exponent. So I'm able to simplify. And on the other side, on the right side, we are also able to simplify these x's as 1x. And because these parentheses are exactly the same in the inside, the group is the same, x squared minus 7. We can apply the rules for exponents to add those exponents. So what would happen if you take this parenthesis down, and because it's the same parentheses, you can add those. You would have 1 over 2 plus 1 over 2. You can add them if you take the parentheses on the numerator down. So if you do that, you would have the same parentheses with the same x squared plus minus 7 with an exponent 1. I'm making an addition of these two exponents. This is also a very good answer. This is actually a final answer. This is perfect. But when we have algebraic functions at the end, you usually want to add them just to have an even more concrete answer. So that's what I'm doing in this last part. From here to here, the only thing that I'm doing is adding those fractions to actually get to the final answer that you have in the square. So check out this exercise in your own time and compare with the last one. And hopefully you have more clear how to use these two rules, the rules for logarithms and natural logarithm, how to use them alone in a very simple natural logarithm, of how can you combine it with product rule. How can you combine it like this when you have a product rule in the inside of the logarithm, or when you have the product rule at the very beginning. So hopefully that's more clear for today, and I'll see you soon.